Good morning everyone. My name is Zarni. Today I am going to discuss about elementary calculation for energy consumption and power factor. Introduction to energy consumption. Definition of energy consumption. Energy consumption refers to the total amount of electrical energy consumed by a device or system over a specific period of time. It is often measured in kilowatt hours, which represents the energy used by a device with a power rating of 1 kilowatt over the span of 1 hour. Formula for energy consumption. Energy consumption kilowatt hour equal to power kilowatt into time hours. Example, a 1 kilowatt device running for 3 hours consumes 3 kilowatt hour of energy. Units. Kilowatt hour is the standard unit of energy consumption indicating how much electricity has been consumed. Power consumption, active power. Definition of active power. Active power or real power is the actual power consumed by a load to perform usual work. It's the component of the total power that does the real work in devices like motors, lights, or heating elements. Formula for active power P. P is equal to V into I into cos phi. V is equal to voltage in volts. I is equal to current in amperes. Phi is equal to phase angle between current and voltage. Example, for a device with a voltage of 220 volts, a current of 5 ampere and a phase angle of 0 degrees, ideal case, the active power would be P is equal to 220 into 5 into cos 0 degrees is equal to 220 into 5 is equal to 1100 units. Watts, the basic unit of active power. Apparent power. Definition of apparent power is apparent power is the total power supplied to a system consisting of both active and reactive power components. It represents the total electrical power, both real and reactive, drawn by the load. Formula for apparent power S is equal to V into I. Apparent power is measured in volt amperes, no watts. Example, for the same device with 220 volts and 5 amperes, S is equal to 220 into 5 is equal to 1100 volt amperes. Reactive power. Definition of reactive power Q. Reactive power does not perform any useful work but is necessary for maintaining the electric and magnetic fields. In devices like motors and transformers, it alternates between the source and the load, creating a phase difference between voltage and current. Formula for reactive power Q. Q is equal to V into I into sin phi. Example. For a system with voltage 220 volts, current 5 amperes and a phase angle of 30 degrees, Q is equal to 220 into 5 into sin 30 degrees is equal to 220 into 5 into 0.5 is equal to 550 var. Units volt ampere reactive. A unit used to express reactive power. Power factor. Power factor is the ratio of real power to apparent power in an electrical system. Real power P, the actual power consumed to do useful work, measured in kilowatts. Apparent power S, the total power supplied to the circuit, measured in kilovolt amperes. It includes both real and reactive power. Formula for power factor is equal to real power kilovolt by apparent power kilovolt amperes. Example, if a device uses 1 kilovolt of real power and requires 1.2 kilovolt amperes of apparent power, the power factor is PF is equal to 1 kilovolt by 1.2 kilovolt ampere is equal to 0.83. This means 83% of the power supplied is being effective. Power factor and energy consumption. Formula for power related energy consumption. Energy consumption kilowatt hour is equal to real power kilowatt into time hours by power factor PF. Example, a 4 kilowatt appliance runs for 6 hours with a power factor of 0.8. First calculate the energy consumption. Energy consumption is equal to 4 kilowatt into 6 hours 0.8 is equal to 240.8 is equal to 30. Interpretation. If the power factor is low 0.8, the system needs more apparent power to perform the same work, leading to higher energy consumption. Power factor and efficiency. Impact of low power factor. A low power factor means the apparent power is needed to provide the same real power, increasing the overall energy demand. It results in higher electricity bills and more losses. Power factor and utility charges. Utility charges for the apparent power kilowatt, and the power factor increases the amount of power you are billed. Improving power factor. Power factor correction. By installing capacitors or synchronous motors, you can improve the power factor. These devices help reduce the reactive power and bring the system closer to an ideal power factor of 1. Benefits. Lower electricity costs, less apparent power needed for the same work. Increased system capacity for the supplied power is used effectively. Improved voltage stability. Example, a power factor with a power factor of 0.6 installs capacitors to improve the power factor to 0.95. This reduces the apparent power and energy consumption. Conclusion. Energy consumption directly calculated by multiplying power kilowatt and time hours. Power factor measures the efficiency of energy usage calculated by dividing real power kilowatt by apparent power kilovolt ampere. Lower power factor increases apparent power and energy consumption. Power factor correction can save energy and reduce costs. Practical applications uses these calculations to estimate energy consumption for different devices and improve system efficiency.